Good morning, folks. This is an abbreviated redo on our class last night that looked at different types of ANOVAs, or brief introduction to different types of ANOVAs, and the concept of ANOVA a little bit better. But due to issues last night with my setup here, we didn't get this recorded, so I'm going to record an abbreviated version to go along with part B that we did get recorded after we had rebooted the system. So that's a little explanation of what we're doing. But this is all about ANOVA, and to kind of sum up a lot of explanation and discussion last night. Essentially, ANOVA is used when we have more than two groups that we're interested in. And when we have perhaps more than one independent variable that we're interested in. Now, remember that independent variables in this setup have to be categorical, and the outcome variable has to be continuous in nature or interval in nature. And so we'll kind of start there and walk through the process. In general, and in order to do that, I'm going to pull up the doc cam here so that I can do a little scribbling. Okay, and so remember that when we're talking about analysis of variance, we're talking about more than two groups. Whether that's determined by one independent variable or a combination of independent variables. And essentially what analysis of variance does is that I'm going to use this box to represent all the variance in a particular experiment. And so the box is all the variance that we're dealing with. And if you'll remember, variance is a value that's determined by sum of squares divided by degrees of freedom, or n-1. And so if this box represents sort of a total variance, and we'll just kind of indicate that the box is total variance. Let me adjust this just a touch. There we go, that's better. The box represents total variance. And if then we have, say, for example, an experiment in which we divide, we're working with three groups, as is the example we'll be doing just a little bit on SPSS. And so we have three groups within that box, say group 1, group 2, and group 3. There is a certain amount of variance that's available, that's explainable, rather, within these different groupings. And so we call that within group variance. And within group variance is, by another name, we can also call that random variance. Now, there may be instances in which the variance within the groups is not random, but we are assuming that those two elements, random variance is most likely to have occurred within the groups. And so if the groups are selected randomly, then we would expect the variance in the groups to be random. Well, as it turns out, total variance is not equal to random variance. In fact, random variance is very often, less than total variance. In fact, it is always less than total variance. And so we're kind of wondering where the rest of that variance went to. And so if we take total variance and subtract out the within group variance, I just do WG, there is a quantity that is left. There's something that's left. And that might be represented by all this space that's in between these groupings. I mean, this is the variance that we don't know about. We don't, we can't measure it directly, and we have no way of doing that measurement directly. And so this variance, we just end up calling it between group variance. And we figure out what that is by subtracting within group variance from between group. And so variance is represented. So now we have the total variance represented within this sample, however big this sample is, that we have then divided into groups in some way. And we know that there's something else out there, that there's this between group variance that we just, we have no way of directly measuring it, but we assume that it does exist. Okay, so keep that in mind. Remember that from discussions earlier, that almost all statistics takes this form, where we have a error term on the bottom and a comparison, or for lack of a better term, we'll just call it a comparison between groups on the top. And in ANOVA, that's represented by a statistic that's called F. And F is the statistic in which we have within group what's called mean squares. That's just the total within group variance divided by the degrees of freedoms for the groups. So if there are 3 groups, then the degrees of freedom for the groups would be 2, and 3 minus 1 is 2. And no, this is within group, my error. Scratch that last statement. Within group is divided by the total number of subjects minus the number of groups. And at the top, we have the between group stuff that we've just figured out. We call that also a mean squares, because between group variance is divided by the number of groups minus 1. So if we have 3 groups, then this would be 2. So between groups divided by within groups gives us between group mean squares. Within groups divided by the number of subjects minus the number of groups gives us within group mean squares. And that gives us an F statistic. Now, an F statistic is not exactly normal. and partially because it doesn't matter negative or plus. And so it's about it's roughly like this. Because it's symmetrical, we don't even bother with the other side. There is no negative side. But the way in which this particular distribution is determined is by two different degrees of freedom, because there's a degree of freedom between groups, in other words, number of groups minus one, and there's a degree of freedom within groups, which is basically the number of subjects minus total number of subjects minus the number of groups. And that's the S statistic. That's the ANOVA. Now, there are 2 or 3 different types of ANOVAs. The simplest one is called one-way. And that's when we have one categorical independent variable, which is really sort of a cause and effect sort of thing. So this is the cause. And we have one continuous dependent variable, which we will call in sort of a causal notion, the effect. And that's one way. When we have what's called a factorial analysis, is when we have two categorical independent variables. We still just have one continuous dependent variable, and one that we will eventually look at, but not necessarily in this discussion. Get something out of the way here. We will have what's called multivariate. In which we have two or more independent variables, categorical, and we have two or more continuous dependent variables. And we will eventually get to multivariate, but not in the next few sessions. Now, within the factorial, there's another way of dealing with information there, but we'll talk about that when we do the analysis. And that's when we do a covariate analysis of variance, analysis of covariance, where we're trying to control for the effects of some variable that we have information on, but we don't really care about. In other words, we want to remove any effect that it may have from the analysis. And so with that, I'm going to load up the file. So I'll stop this share. The analysis of variance, the file that we'll be using is a file from last evening that was your first formative assessment, but one that we did a little bit of recode on, in that we created some numeric coding for groups and numeric coding for gender. And so I'm going to open that example or that data file with the recodes. I'm not going to talk about how to do recodes in this particular block. I'll put that in a separate video that I'll share a bit later, but not today. And so let me go share that data file. I have put this data file up in As You Learn, so it's called the the formative assessment recoded file used in the ANOVA example. Now, in order to do a one-way, let me get this where I can actually see it. In order to do a one-way analysis of variance, and we're going to look at the change to score, and we're going to do a one-way based on group. Here is the alphanumeric grouping, or group one over here, either one. We'll just use the alphanumeric for this one. And so we'll do a analysis comparison of means. Now, the only ANOVA procedure that's in a comparison of means will be the one-way. For all the others, we'll use the next line down, which is general linear model. So we're going to use one-way ANOVA. Change to is our dependent variable. Group one is now our factor. That's the independent variable. ANOVA calls it a factor. We're going to add a post hoc test. We'll add a Tukey, that's the default. And we can have a little bit of a discussion later about the other types, but we'll add the Tukey, which is the default. And we'll add some descriptive stats so that we'll have information on the groups. And you'll notice the level is, confidence interval is 95%. That's the 0.05 error. And so we will run that example. I'm going to have to unshare the data file to share the output screen. So that's what I'm doing right now. And you'll notice here we have in the output screen, we've got, let me make this a little bit bigger. We have the three groups for change to. We have the N in each group. We have the total N. Here's the mean, the standard deviation, standard errors. So we know that we can look at the mean, and we know that the mean for group one is 0.27, the mean for group two is 1.14, and the mean for group three is 3.41. When we go to the ANOVA section, once again, we have the between groups and the within groups. Sum of squares between groups divided by groups minus 1, 2, gives us a mean square of 57. Sum of squares within groups, which is the total number of folks within groups, is 498.33 divided by the total N minus the number of groups. Divided by degrees of freedom, which is total N minus the number of groups. So 66 minus 3 groups, 63, gives us a mean square of 7.909. And so when we divide the between group stuff by the within group stuff, we end up with an F of 7.3 and a significance level of less than 0.001. So it is a significant outcome. When we go to the comparisons, the post hoc comparisons, to figure out what the differences are, these are always, we know that 1 was less than 2 and 2 was less than 3. And so when we look at the significance level here, we know, well, let's just go down to 3. We know that 3 has the highest outcome. It is significantly higher than 1. It is also significantly higher than 3, than 2. And we know that 2 is significantly higher than 3. And so when you think about how these things lay out, it's kind of like 2, if we were to stack them, we'd say 1, 2, 3. And so 1 is significantly less than 2, but both 1 and 2 are significantly less than 3. And so if the magnitude of the number matters, then we would say that, okay, it looks like, there are significant differences between all the groups, with group 3 having the most positive or the highest outcome. Now, if some of the groups are similar to each other, they'll show up in this homogeneous subset here. And in fact, what it shows is that although there are differences, there are no significant differences between groups 1 and 2. 1 and 2, no significant differences. And so therefore, this treatments 1 and 2 could be grouped together and treated as the same, and treatment 3 is significantly higher than the other 2 groups. And so that's what we can say from the discussion of this one-way comparison of the change scores by groups. Now, the second instance in which we have stop the share on that and go to back to the data set and share out the data set again. Remember, we said that the other opportunity in which there would be more than 2 groups would be if you have more than one independent variable. And so if we looked at group with 3 groupings and gender with 2 groupings, male, female, then when you put those 2 together and display them in a matrix, you have 6 groups. In other words, you have 3 groups that is comprised each of 2 different genders. And so we have 6 groups. And so once again, we're back into ANOVA. Well, the analysis now, because we have more than one independent variable, falls under what's called the general linear model, which covers a lot of territory. And so we'll look at univariate. Univariate means we only have one dependent variable. And so we have, once again, change 2 as our dependent variable. Our fixed factors, which are the way in which ANOVA talks about independent variables, would be group 1, the recoded variable, and gender 1. Notice we're not going to do post hocs. We're just going to do the descriptive, so we'll have some way of looking at that a little bit better. Well, as a matter of fact, we will do post hocs. And once again, we'll do a post hoc for group 1, and we'll do a post hoc for gender, and we'll opt for Tukey once again. And we'll run that. Let me go back over to the output file. And so now we have this univariate analysis of variance. There's group 1, group 2, or excuse me, group one and gender one, 3 groups, 2 genders. Here's the table with all of them mixed together. And so we have, you know, for group 1, we have male and female. For group 2, we have male and female. For group 3, we have male and female. And then all the totals. Then we have what are called the test of between subjects effects. Once again, group 1 is significant. But gender 1 is not. Now, and combination, the interaction between group and gender is not. Now, group 1 and gender 1 are called main effects, and group 1 by gender effects are called interaction effects. And so from this, we're able to know that group 1 is still the only significant effect here. Gender doesn't have an impact, and any interaction between group and gender doesn't have a significant impact. Now, the other thing we're able to know is R squared down here is that grouping, in other words, the putting subjects into 3 different groups, accounts for about 23%, because the R square is 0.23, that's actually at a percentage. It accounts for 23% of the total variation. So we're able to explain at least 23% of the total variation by the fact that we put students into groups, but that doesn't, you know, gender doesn't help us any, and any interaction doesn't help us any. And once again, we have all these multiple comparisons down here. Was just like the post hoc changes before. Once again, there's the difference between group 1 and 3, the difference between group 2 and 3, a little bit significant difference, and the group difference between groups 3 and both the other groups. So it's the same outcome as before. Now, we go back to the chart here, to the home screen, because the other thing that we talked about, and we talked about that in part B, is using the same analysis, but taking out any effect of gender at all, because although gender didn't have a significant effect, it did have, you know, it could have had some impact on the scoring for change 2, and so we took that out. So that is covered over in part B of this video, which has already been posted. So that's essentially an abbreviated version of what we talked about yesterday evening in the first part of the session that I did not get a chance to get recorded. So this should fill in that void.